Hello and welcome to the quiet cosmos. Tonight the tour stays close to home, moving outward from the sun toward everything that circles it. Rock, metal, ice and gas, laid out across one long, calm evening. The question underneath every stop is a simple one. If you picked up a handful of material from 8 very different worlds, you might expect none of it to look alike. It does. And finding that resemblance, piece by piece, is the whole of tonight's slow journey outward. Before the first stop, one small request. If a long, unhurried tour through everything the sun ever gathered sounds like good company for falling asleep, a quiet like or a tap on subscribe helps this channel find more of the people already searching for exactly this kind of slow science. It costs nothing and takes only a moment, and it is the only thing I will ask of you all evening. Some rocks in our collection have never belonged to a planet at all. They are called chondrites, and unlike the rocks under your feet, nothing about them has ever been melted down or folded back into something larger since the day they first came together. A piece of ordinary crust has been through mountains, oceans, heat and pressure more times than anyone could count. A chondrite has not. It sat quietly through the whole of that history, untouched, while planets rose and wore away around it. That makes it less a rock than a record, closed the moment it formed and never reopened. A single one of these sits in hand at the start, plain and unremarkable to look at. The story can wait. The evidence cannot, because it is sitting in drawers in museums right now, waiting for someone to ask what it remembers. What it remembers is older than every planet it now outlives. Inside many of these chondrites sit small, round beads, each barely the width of a match head, called chondrules. At some point long ago, each one was fully molten, a tiny floating droplet of rock with no vessel to hold it. And then it cooled and hardened within minutes rather than years. Melting a mineral droplet that fast, in open space, with nothing nearby to melt it slowly, is not an easy thing to arrange. Furnaces do not do this. Slow cooling near a young star does not do this either, because slow cooling leaves a very different crystal structure behind, one that chondrules do not have. Whatever event flashed through the early mixture, hot enough to melt rock and gone again inside minutes, has never been pinned down with any certainty. Meteorite collections hold uncountable numbers of these beads, each one a small, sealed record of an event nobody has fully explained. Cut a chondrite in half, and a slice packed with these beads looks almost like a scoop of solidified porridge. Hundreds of tiny spheres pressed together inside a dark matrix. They sit there, glassy and round, waiting on a question nobody has managed to answer yet, and perhaps will not for a long while. Between the chondrules sit paler patches, rich in calcium and aluminium, and these are thought to be the very first solids the mixture ever produced. Almost everything else in a young cloud of gas and dust stays vapor until it cools past a certain point, and these particular minerals are the first ones able to condense out of that vapor and hold their shape as something solid. Chemists call them refractory for exactly that reason. They resist heat better than nearly anything else in the mix. Long before there was a planet, or even a proper disk of debris to build one from. There were these small, pale grains sitting alone in the heat, the very first stubborn crumbs of matter in the whole system. Under a hand lens, they resemble little more than flecks of chalky white scattered through darker rock. Their name comes from a chemistry that geologists find useful well beyond meteorites, describing any mineral stubborn enough to hold its shape under extreme heat. What they mark is a beginning, the first moment anything in this system stopped being gas and became something you could, in principle, hold. Those same pale inclusions carry the earliest date anything in this system has ever produced, close to 4,567 million years. This is not the age of the Sun, and it is not the age of any planet, because none of the planets had begun to gather yet. It is the age of the first solid crumb, the very first thing in the whole mixture willing to stop being vapor and hold a shape. Every rock, moon, and world that came afterwards is, in that sense, younger than these small, pale grains, sometimes by many millions of years. Meteorite hunters treat that number carefully, because it is not a guess dressed up as a fact. It is closer to a birth certificate for the whole system, written not in ink, but in mineral grains that have sat in the dark, unchanged, since the day they hardened. Nothing since has managed to erase it. Buried inside the very same rocks are grains that are, by any reasonable measure, older than the solar system itself. They are tiny crystals of silicon carbide and graphite, and their chemistry does not match anything the Sun's own mixture could have produced. Instead, it matches the output of other, older stars entirely. Stars that lived and died long before our own began to gather. Somehow, these small crystals survived that whole earlier ending, drifted through open space for who knows how long, and were folded, unchanged, into the mixture that eventually became this system. They are older than the Sun, older than the Earth, older than every planet in the system that formed around it. Laboratories identify them by isotopic ratios so unusual that no process inside this system could plausibly have produced them, leaving an outside stellar origin as the only workable explanation. Astronomers call them pre-solar grains, a plain enough name for something genuinely strange, a handful of stardust from a star that no longer exists, sitting quietly inside a rock you could hold in one hand. Add all of that together, and a rough bookkeeping of the original mixture starts to appear. Hydrogen and helium make up almost the whole of it. The same two light gases that dominate the Sun and every star like it. Everything else, every atom of rock, metal, carbon, and ice that ever became a planet, moon, or grain of dust, adds up to only a couple of parts in 100 of the total. That is the entire allowance the system had to work with for building anything solid. 2 parts in 100 does not sound like much, and it is not. Compare that thin allowance against the sheer scale of the whole mixture, and the imbalance becomes almost stark. Nearly everything is light gas, and only a modest remainder was ever solid enough to matter. And yet from that thin remainder came every rock underfoot, every mountain, every metal core, every quiet ocean, every rocky world patient enough to hold on to any of it at all. Here is the discovery the whole tour is built around. Take the outer layers of the Sun, the part we can actually measure by splitting its light into a rainbow, and compare it, element by element, with the composition of an ordinary chondrite. Strip away the gases too light for a small rock to hold onto, and the two lists match remarkably closely. The same relative amounts of iron, magnesium, silicon, and dozens of rarer elements besides, in a star very nearly 1.4 million kilometers across, and in a stone that fits in a coat pocket. Two objects, utterly unlike each other in every visible way, sharing one recipe. The simplest explanation is also the correct one. Both were drawn from the same cloud of gas and dust at the same time, and neither one has strayed far from that original mixture since. Every world of rock, metal, ice, or gas in this system is a variation played on this one shared recipe. Oxygen is not one single ingredient, chemically speaking. It comes in three slightly different varieties, sitting side by side in the same mixture. And the ratio between them barely changes once a rock has formed. That stability turns the ratio into something like a fingerprint, or better, a postal code. Wherever a rock or planet condensed, it kept the exact isotopic ratio of that particular patch of the mixture, more or less permanently. Earth and the Moon share a postal code so precise that the two are almost impossible to tell apart by this measure alone, whatever else separates them. Mars carries a different one. The parent body of Vesta, one of the largest objects in the asteroid belt, carries a third, distinct from both. None of this required watching anything form. The measurement itself is delicate work, carried out with instruments sensitive enough to separate isotopes differing by only a single unit of mass. It only required comparing the isotopes already locked inside rocks collected from each of these places, and letting the numbers speak for where each rock was made. Sort enough meteorites by a second isotopic marker, this time hidden in metals like titanium and chromium instead of oxygen. And a pattern falls out cleanly. The whole collection splits into two large families that almost never mixed with one another. One family carries chemistry that points to material collected closer in, nearer the young sun's fiercest heat. The other carries chemistry that points to material collected farther out, in the colder, outer reaches of the mixture. For a long stretch of the system's early history, these two groups appear to have stayed almost entirely apart, as if something kept a partition standing between them. They are not different clouds. Even now, sorting a large meteorite collection by this single measurement is often enough on its own to reveal which half of the young mixture a given rock belonged to. They are one cloud, evidently, with an internal wall running through it, and every rock that formed on either side kept its own family's signature for good. Put all of this together, and a shape starts to emerge before a single planet has even entered the story. There was one original mixture, not many, and every rock and grain examined so far traces back to it. But that one mixture was never smooth or uniform from edge to edge. It had regions, tendencies, pockets that never fully blended into their neighbors. What comes next is not really the story of how planets were built from scratch. It is the story of how one uneven mixture got sorted, region by region, into worlds that look nothing alike on the surface, and yet, underneath, still answer to the very same set of ingredients. That unevenness required no outside intervention to explain it. Ordinary distance and ordinary heat, acting slowly over a long stretch of early history, were apparently enough on their own. Sorting, not creation from nothing, is the theme worth carrying forward from here. Water is not equally welcome everywhere in a young system. Close to a newly lit star, heat keeps water as vapor, no matter how much of it is floating around. Only farther out, past a certain distance, does it turn cold enough for that same vapor to freeze solid and stay frozen. Astronomers call that distance the frost line, sometimes the snow line, and it works less like a wall and more like a long, slow threshold running in a ring around the young sun. Cross it heading outward, and the available building material changes completely, not in kind, but in quantity. Suddenly, water is something you can build with, instead of drifting past as gas. The line itself was never solid or visible. It was a temperature, a threshold separating one part of the mixture from another, and every rock and world that formed nearby still carries the mark of which side it happened to be on. As the young mixture cooled, different materials solidified out of it in a fairly predictable sequence, dictated by how much heat each one could tolerate before turning solid. The toughest minerals and raw metal came first, condensing while everything nearby was still far too hot for anything softer. Silicate rock, the ordinary stony material that makes up most planetary crusts, came next, once temperatures had eased a little further. Ice of any kind came last of all, and only in regions that had cooled enough to let it stay solid instead of boiling straight back into vapor. This order is not a guess built after the fact. It follows directly from ordinary chemistry, the same rules that decide what freezes first in a glass of cooling liquid, only stretched across a system many millions of kilometers wide and applied to an enormous cloud of dust instead of a drink. A patch of the mixture sitting close to the center might never see ice condense at all, however long the system waited, because the local temperature never dropped far enough. Distance from the center, translated into temperature, decided the menu at every stop. Water is only the first and closest of several different freezing points scattered through the outer mixture. Ammonia has its own line, farther out again, where it becomes cold enough to solidify. Methane freezes at a colder threshold still, farther out than ammonia. Carbon monoxide, one of the most stubborn gases in the mixture, will not sit still as a solid until the surroundings are colder yet, out where almost nothing else has managed to freeze at all. Each of these thresholds sits at its own particular distance, nested one beyond the next, like a set of rings spreading outward from the warmth at the center. So when the word ice comes up loosely from here on, it rarely means only water. Laboratory experiments recreating these conditions confirm the order fairly reliably, freezing each candidate material in turn as the surrounding temperature is lowered step by step. Depending on exactly how far out a given world formed, ice can mean water, or ammonia, or methane, or carbon monoxide, frozen solid and waiting, each one a slightly different kind of cold. Crossing the frost line does something dramatic to the sheer quantity of solid material available for building anything. Inside the line, only the toughest minerals and metal can stay solid, and that leaves a fairly thin allowance of raw material to work with. Outside it, water and the other ices join the available inventory, and because there was originally so much more ice than rock in the mixture to begin with, the total amount of solid, buildable material jumps by several times over. The underlying recipe did not change at that boundary. The same atoms, in the same rough proportions, were sitting on both sides of the line the entire time. That single change in state, from vapor to solid, and nothing else, is doing almost all of the work in this part of the story. What changed was simply which of those atoms were allowed to be solid instead of vapor. And that single change in state turned a thin allowance of building material into a much thicker one, waiting just beyond the threshold for anything patient enough to gather it. That extra allowance of solid material beyond the frost line set the pattern for how the largest worlds in the system were assembled. Building began the same way everywhere, with small grains sticking together into pebbles, pebbles into boulders, and boulders slowly into a solid core. Beyond the frost line, though, that solid core had far more raw material on hand and could grow considerably larger and faster than anything forming closer in. Once a solid core out there crossed a certain size, its own gravity became strong enough to start pulling in the surrounding gas directly, gathering an atmosphere far heavier than the rocky seed underneath it. Inside the frost line, cores generally never grew large enough to manage that trick at all. Not every core beyond the line managed the trick either. A great many stalled at a modest size, too small ever to start pulling in gas of their own. The order, everywhere it worked, ran the same way. Solid seed first, gas afterwards, and only for the seeds that grew large enough, quickly enough to catch it. Gathering that gas envelope was not a task with an open deadline. The gas in a young system's surrounding disk does not last indefinitely. It drains away, blown off by the young star's own radiation and carried off in stellar winds, disappearing within a few million years of the system's earliest beginnings. A solid core that grew large enough to start pulling in gas while that gas was still available could build itself an enormous atmosphere. A solid core that grew large enough only after the gas had already thinned and departed was left with nothing to gather but its own bare rock and ice, however impressive that core might otherwise have been. Timing mattered every bit as much as location. Grow fast enough, in the right place, and there was a whole atmosphere waiting. Once that gas has gone, it does not return. Whatever a core has managed to gather by then is, for practical purposes, the envelope it will keep. Grow just a little too slowly, and the window had already closed by the time you were ready to use it. Put those last two ideas together, distance from the frost line and speed of growth, and the difference between a gas giant and an ice giant stops looking like a difference in recipe at all. Both kinds of world drew on the same original mixture of rock, metal and ice sitting beyond the frost line. What separated them was how large a solid core each one managed to build, and how much of the available gas was still around by the time that core was ready to gather it. A core that grew quickly and early could pull in gas by the enormous quantity, becoming a true gas giant. A core that grew a little later, after most of the gas nearby had already thinned out, was left mostly with ice and rock, dressed in only a modest remaining atmosphere. Neither kind of world is, strictly speaking, more successful than the other. Each answered to a different combination of distance and timing. Same ingredients, same rough neighborhood, different arrival time. The frost line itself was never fixed in place for the whole of the system's early history. Early on, while the young sun still burned brighter and the surrounding disk still held plenty of warmth, the line sat farther out from the center than it eventually would. As the disk thinned and cooled with age, that boundary crept steadily inward, retreating toward the sun a little more with each passing stage. A patch of the mixture that once sat safely inside the frost line, warm enough to keep ice from surviving there for long, could later find itself on the cold side of a line that had simply moved to meet it. Models attempting to track that inward drift in detail still disagree on exactly how far and how fast the boundary moved, though the general direction, inward over time, is not seriously disputed. The boundary drifted through the disk like the edge of a slow tide, and whatever happened to be standing nearby when it passed had to answer to whichever side it landed on. This slow drift matters a great deal for one particular region, the asteroid belt. Rather than sitting neatly to one side of the frost line for the whole of its history, the belt occupies almost exactly the stretch of space the line drifted back and forth across while the system was still assembling itself. That single detail explains something the belt would otherwise make little sense of. Material there that looks thoroughly dry sits right beside material that looks thoroughly water-rich, close enough that a short journey separates the two. They were never sorted cleanly into two neighborhoods to begin with. A rock sitting only a short distance from its neighbor in the belt today may, in that sense, have condensed under noticeably different conditions because the boundary had shifted between the two moments. They sat instead on either side of a boundary that never held still, and their differences record less a fixed rule than a moving one, caught partway through its own slow retreat. Step back from all of it, and one plain number does most of the explaining. How far a given patch of material sat from the center, translated by ordinary physics into a temperature, decided which ingredients were allowed to stay solid there and which were not. That single decision, repeated at every distance across the young mixture, produced the entire menu available across the system. Dry rock close in, ice-rich material farther out, and a long, slow-moving boundary that spent the early history of the system drifting between the two. No separate story is needed for each world visited from here on. None of this required a planet to already exist before the sorting began. The sorting itself came first, and the worlds followed from wherever it happened to leave them. Distance did the sorting on its own, one straightforward temperature at a time, and everything that followed was simply what each patch of material was left holding when the sorting stopped. Move in close to the sun, well inside the frost line, and the inventory available for building anything shrinks down to two ingredients only: rock and metal. Ice never had a chance to survive there in any useful quantity, boiled away by heat long before it could hold together as a solid grain. 4 worlds eventually formed out of that reduced inventory, the 4 rocky worlds closest to the sun, and every one of them is, in the plainest sense, made from whatever a hot, ice-free stretch of the mixture had left to offer. Mercury, Venus, Earth, and Mars are the 4 names most often given to that dry harvest, each one a different portion of the very same hot recipe. None of them carries a meaningful ocean's worth of water from its own original formation. None of them carries a thick shell of gas gathered directly from the surrounding disk. Even the least studied of the 4 still fits the same basic description: dry rock and metal, gathered from a stretch of the mixture where nothing softer ever had a real chance to survive. What each one carries instead is rock, layered over metal, built from a corner of the mixture too warm for too long to keep anything softer than stone. Add the 4 rocky worlds together, and the whole group weighs only a little under twice the mass of one of them alone in Earth's own terms. A modest total for 4 entire worlds. That is not because the inner mixture was somehow thin or lacking in material to begin with. The 2 parts in 100 set aside for solids applied everywhere, inner region included. It is because the hot, dry zone available for building rocky worlds was narrow, squeezed tightly between the sun's own fierce heat and the frost line farther out. A narrow zone has less raw material passing through it than a wide one does, whatever the overall richness of the mixture happens to be. The dry half of the system came out light not because the ingredients ran short, but because the workshop itself was small. Cut deep enough into any of the 4 rocky worlds, and the same basic structure appears every time. Metal concentrated at the center, lighter rock arranged above it in layers. That kind of clean separation does not happen by accident, and it does not happen to material that was simply piled up cold and left alone. It happens only when a whole body has been thoroughly melted at some point, turned liquid enough throughout for heavy metal to sink under its own weight, while lighter rock floated upward to take its place. So every one of these 4 worlds, without exception, carries the signature of having been, at least once, entirely molten. That is a striking thing to say about 4 worlds that have been solid rock for billions of years. Even a modest body, once fully molten, will separate this way given enough time, because the difference in weight between metal and rock is large enough to win out eventually. Somewhere in each one's early history, long before it hardened into the shape it wears today, it was, for a stretch of time, closer to liquid than to stone. Melting 4 separate worlds thoroughly enough to sort metal from rock takes a serious source of heat. And the sun itself is not a strong enough candidate for the job at that distance and that early stage. The leading suspect, instead, is an unstable form of aluminium, present in only tiny amounts throughout the original mixture, which breaks down steadily and releases warmth as it does. On its own, that sounds too faint to matter, but this particular form of aluminium decays away over a span of well under 1 million years. And while it lasts, it can warm a small rocky body from the inside out surprisingly effectively. A body assembled early enough to still hold a decent supply of it could heat itself thoroughly, entirely from within, with no help from sunlight at all. It was never a dramatic source of heat. It was patient, steady, and, for a while, everywhere. That warming supply came with a strict deadline attached, because the unstable aluminium it depended on was disappearing the whole time, decaying away whether anything used it or not. A body that gathered together early, while a healthy supply of it still remained in the mixture, could heat up enough to melt and sort itself properly. A body that assembled a little later, once most of that supply had already decayed away to nothing, missed the window entirely and stayed cold, unmelted and unsorted from the very start. Those late arrivals are, in effect, the very chondrites described earlier. Material that formed too late to catch the last of the heat, and so never melted, never separated into layers, and never lost the record of its earliest self. The line between the two outcomes was not gradual. A difference of 1 million years or two in a young body's assembly could tip it from one fate to the other entirely. Timing decided, in each case, whether a body became a smooth, layered world or stayed a rough, unsorted stone forever. Not every rocky world grew to the size its position ought to have allowed. and the clearest example sits fourth from the Sun. Mars carries only a modest fraction of the mass that most models of the inner zone expect a world at that distance to reach. A shortfall too large to explain away as ordinary variation. It is a specific, quantitative gap between how large the available material there should have let a world grow and how large the world that actually sits there turned out to be. Researchers refer to this shortfall, somewhat dryly, as the Mars problem. And the name has stuck for decades because no explanation offered so far has fully closed the gap. Somewhere in the assembly of that particular stretch of the inner disk, something interrupted the usual process, and precisely what remains an open question. Most explanations offered for that shortfall converge on roughly the same idea, even where they disagree on the details. Solid material in that stretch of the inner disk appears to have become scarce unusually early, well before a world there had time to finish gathering it. Some point to how quickly the very earliest solid seeds could have formed at that particular distance. Others point to how efficiently later collisions there managed to stick pieces together instead of cracking them apart. What none of them offer so far is a single settled account that the wider community has agreed on outright. The shortfall itself is not in doubt. Meteorite chemistry, orbital dynamics, and the plain size of the world in question all point the same way, toward a stretch of the disk that ran short of building material sooner than its neighbors did. Whichever mechanism eventually wins the wider debate, the underlying observation itself is not in question. This particular stretch of the disk had less to work with than its neighbors did. Exactly why it ran short first remains, for now, a genuinely open question. Closest of the four rocky worlds to the Sun, Mercury carries a heavier share of metal relative to rock than any other rocky world in the entire system. In a body built the ordinary way, from the same rough mixture as its neighbors, metal and rock should settle into roughly the same proportion nearly everywhere in the inner zone. Mercury does not follow that pattern. Its balance leans far more heavily toward metal than plain condensation from the local mixture can easily account for. And no single straightforward version of the ordinary recipe reproduces that lean without some extra step added in. Perhaps an early violent encounter stripped away much of its outer rock at some point, leaving the metal behind in a greater relative share. Perhaps the local mixture ran unusually rich in metal to begin with, for reasons not yet understood. Either way, something in Mercury's particular corner of the mixture did not play by quite the same rules as everywhere else. Earth and its moon share that same oxygen postal code so precisely that laboratory measurements struggle to tell the two apart at all. For two separate bodies, one considerably larger than the other, to match that closely is unusual enough to demand an explanation. Because most pairs of worlds, even close neighbors, carry small but measurable differences from one another. Whatever account of the Moon's origin eventually wins out among the several currently debated, it has to explain that near-perfect match convincingly, not merely noted in passing. A glancing collision that mixed material thoroughly between the two bodies is one popular way of accounting for it. A slower, gentler process of shared formation is another. Careful laboratory work over recent decades has narrowed the range of plausible explanations considerably, even without settling on a single winner outright. The debate over exactly how continues in journals rather than headlines, but the underlying measurement that started it, one shared postal code, two very differently sized worlds, has stood steady through decades of increasingly careful checking. Earth's own oceans sit a little awkwardly against the general rule for the inner, dry half of the mixture. Earth formed well inside the frost line, in the same hot, ice-free stretch of the disk that produced the other three rocky worlds, and water could not have stayed solid there for any meaningful length of time during that early, warm stage. Whatever small trace of water vapor might have briefly touched that region should, by the logic of the frost line, have boiled straight back off rather than settling permanently anywhere on Earth's early surface. And yet oceans plainly cover most of the planet today and have done for a very long stretch of its history. Somehow, a world built in the dry half of the mixture ended up carrying more water than the simple recipe for its own neighborhood ever promised it. That gap between where Earth formed and how much water it now holds remains the quiet puzzle underneath every ocean. One careful way of checking where that extra water actually came from relies on a small variation hidden inside every water molecule. Alongside ordinary hydrogen, a heavier version called deuterium turns up in trace amounts, and the ratio between the two varies depending on where and how the water first formed. Measure that ratio in Earth's oceans, then compare it against the same ratio measured in various outside candidates, and a pattern starts to emerge. Earth's own ratio sits closer to certain stony meteorites than it does to most of the icy comets measured so far. That single comparison does not settle the whole debate outright, because plenty of individual candidates still fall outside the expected range either way. No single meteorite settles the question by itself. It is the pattern across many samples, weighed together, that points the comparison one way rather than another. It does, however, point the finger less at distant icy visitors and more at rocky material from somewhat nearer neighborhoods, quietly carrying trace amounts of water bound up inside minerals instead of as loose ice. Draw the four rocky worlds together as one group and a clear picture settles into place. They are the dry half of the original mixture, built entirely from whatever a narrow, hot stretch of the disk had left after every trace of ice had boiled away. Most of the water any of them carries today, and Earth carries by far the most, appears to have arrived afterwards, imported from somewhere beyond the boundary that kept this whole zone dry in the first place, though a smaller share may have been present in the local rock and metal all along. Rock and metal are native to this stretch of the system. Everything soft, everything liquid, everything that pools and flows across a rocky surface is, in the strictest sense, largely a visitor from the far side of a line the inner worlds themselves could never have crossed. That is the quiet truth sitting underneath four planets most people assume were built exactly where they now stand. A stretch of space between the rocky worlds and the giants farther out holds a scattered ring of smaller bodies known as the asteroid belt. And one persistent piece of folklore claims it is the wreckage of a planet that once stood there and later broke apart. The actual numbers rule that out almost immediately. Gather up every object in the entire belt, weigh the lot together, and the combined total comes to only a small fraction of the moon's own mass. Nowhere near enough material to have ever made a proper planet in the first place. There was, in other words, never quite enough there to build with. Early observers, working only from what a telescope could show them, once genuinely suspected a missing planet had shattered here, and the name stuck long after that particular idea was abandoned. What sits in the belt today is closer to raw, leftover stock than to rubble, material that never finished the job of becoming a single, larger world, and not material left behind after one was destroyed. The largest single object in the belt, Ceres, is also the roundest, pulled into a smooth, near-spherical shape by its own modest gravity, instead of staying lumpy and irregular the way most of its smaller neighbors do. It carries a noticeably large share of ice for something sitting this close to the inner rocky worlds, more in keeping with material from farther out past the frost line than with the generally dry stock filling most of the belt around it. Sitting where it does, surrounded mostly by drier neighbors, Ceres looks less like a native resident of this stretch of the mixture, and more like a guest that wandered in from the wetter side of the line and stayed. Its presence here, mixed in among drier company, is itself a small clue about how far material moved before the belt finally settled into whatever order it holds today. A short distance from Ceres sits Vesta, and the two could hardly be more different from one another. Vesta is dry, not icy, and its surface preserves an ancient crust of hardened lava, cooled solid long before anything else in the belt settled. That crust is a strong sign that Vesta once melted thoroughly enough to separate metal from rock, exactly like the rocky worlds nearer the sun, before whatever process was building it stopped partway through. Call it a protoplanet, if the word fits. A body that reached the melting, layering stage a full rocky world eventually reaches, and then never gathered enough further material to grow any larger than it already was. Its surface still shows the pale scars of that ancient stopping point, a record of a formation cut short, not one that never began. It stalled, essentially, at a stage the four inner worlds managed to grow well past, leaving behind a small, dry, fully differentiated body frozen at an earlier chapter of the same story. Pieces of Vesta are not confined to the belt itself. A whole family of meteorites recovered here on Earth has been traced, chemically, back to that single parent body with real confidence. Their mineral makeup, their oxygen signature, and their overall composition all line up closely enough with material studied directly on Vesta's own surface that few researchers doubt the connection any longer. Some ancient collision, long before anyone was watching, chipped fragments loose from Vesta's outer layers and sent them tumbling across the inner system, eventually to be caught by Earth's own gravity, and to fall as ordinary-looking stones. Anyone holding one of these particular meteorites is, in a very literal sense, holding a fragment of that one stalled protoplanet in the belt, delivered here across a gap of many millions of kilometers and a great deal of time. Survey the belt as a whole, and its material sorts itself by distance in a familiar way. Drier, rockier types cluster mostly toward the inner edge, closer to the warmth of the rocky worlds. Darker types, rich in carbon and holding water bound up chemically inside their minerals instead of as visible ice, cluster mostly toward the outer edge, closer to the giants beyond. These are the same two isotopic families, sorted by that same original postal code, sitting here side by side within a single narrow ring rather than scattered randomly through it. Telescope surveys covering thousands of belt objects at once have mapped this contrast directly, and the handful of asteroids visited close up by spacecraft confirm the same pattern from close range. The belt, in that sense, is less a single neighborhood than a compressed cross-section of the whole mixture, both families represented within one relatively small stretch of space, still distinguishable from one another after everything that has happened since. That kind of close neighboring is itself worth pausing over. because it tells you something the neat picture of a smooth, orderly mixture would not predict on its own. If every piece of material had simply stayed exactly where it originally condensed, the belt should show a clean, gradual gradient from dry at one edge to wet at the other, with little abrupt change anywhere along the way. Instead, the two families sit closer together and more thoroughly mixed than a purely local origin would explain. Somewhere in the belt's early history, material moved, nudged inward from farther out or outward from farther in, well beyond wherever it first happened to form. The belt was never a sealed neighborhood. It was, and in a slower sense still is, a crossing point, and the mixed company found there today is the plain evidence of that traffic. Whatever kept the belt from finishing the job and gathering itself into a single planet comes down, in the end, to speed. Elsewhere in the disk, small bodies drifting near one another tended to meet gently at low relative speeds, and gentle meetings favor sticking together rather than breaking apart. In the belt, something kept relative speeds unusually high between neighboring bodies, and at high speed, a collision is far more likely to shatter both objects involved than to merge them into something larger. Building requires soft, patient collisions, repeated many times over. The belt, for reasons still argued over among specialists, never settled into that gentler regime for long enough to finish the job. A handful of survivors from that gentler stretch of history remain large enough and intact enough to be studied individually today. Protoplanets that happen to avoid the worst of the grinding. It grew a scattering of stalled protoplanets like Vesta and Ceres, and then, instead of continuing to build upward from there, it turned towards slowly grinding its own material back down. Grinding, rather than building, has left its own kind of records scattered across the belt, in clusters of smaller bodies that share both a common orbit and a matching spectral signature, the particular pattern of light each one reflects. Researchers call these clusters families, and the tightness of the match, in both orbit and composition, points strongly to a single shared origin. One larger parent body, broken apart by some ancient collision, its fragments still drifting together along roughly the same path they inherited from that shattering. Hundreds of such families have been identified and catalogued across the belt so far, each one effectively a fossil crime scene, preserving both the material and the rough orbit of a parent body that no longer survives as a single object. The belt does not just hold leftover material. It holds the wreckage of its own repeated small collisions, still sorted by family long after the fact. A great many of the smaller bodies scattered through the belt are not solid rock at all in any strict sense, but loose piles of rubble, boulders and gravel, held together by little more than their own weak mutual gravity. Two asteroids of exactly that kind, Ryugu and Bennu, both drifting now on paths much closer to the Sun after being knocked out of the belt long ago, turned out on close inspection to be built exactly this way. Dark, uneven surfaces made of loosely packed material instead of a single fused stone. A pinch of that material born in the belt has since been carried back to laboratories on Earth, sealed and kept away from anything that might contaminate it. Loosely packed material like this absorbs an impact instead of shattering outright, which may be one reason bodies built this way have managed to survive as long as they have. What such samples show, still being studied in detail, is material from the belt in a condition almost nobody has ever examined this closely before, gathered instead of merely fallen. Taken together, the belt is not a graveyard and not a planet gone wrong. It is the one stretch of the whole system where the ordinary process of assembly, seed gathering seed, small piece joining small piece, got interrupted midway through and stayed that way, frozen at an early, unfinished stage, and not completed or fully undone. Everywhere else in the system, that same process either finished, producing a proper world, or never really began at all. Only here did it stall in the middle, leaving behind protoplanets, fragments, families and rubble piles, all still sitting close enough together to be read as one continuous, unfinished sentence. Halfway between raw material and a proper world that never quite arrived. A stretch of history that stopped partway through and was simply left that way. Step back out past the belt toward the two largest worlds in the system, and a chemical clue changes the whole picture of how they were built. Measure the balance of heavier elements inside Jupiter and Saturn relative to hydrogen and helium, and both worlds carry noticeably more of that heavier material than the Sun's own outer layers do. The same outer layers used as the baseline recipe for the entire mixture. If either giant had gathered together straight out of the surrounding gas, with no separate solid material involved at any stage, its heavy element balance ought to match the Sun's fairly closely. It does not. Earlier measurements of this kind relied on remote sensing alone. More recent missions have refined the numbers considerably without overturning the basic conclusion. That mismatch points toward a different kind of beginning. A solid seed forming first, sweeping up heavy material well before any large quantity of surrounding gas was pulled in, tilting the final balance away from the Sun's own and towards something noticeably richer in exactly the elements a solid seed would have collected first. Put that chemical clue together with the timing that governs the frost line, and the likely sequence for building a world of this size comes into focus. First, out beyond the frost line, where solid material ran plentiful, a core of ice and rock gathered together, growing steadily until it reached a mass several times that of the whole Earth. Once a solid core crossed that particular threshold, the gathering stopped being gradual and turned into a runaway. Gas fell in faster than the young planet could settle it, wrapping an enormous envelope around the seed within what was, on cosmic timescales, an extremely short stretch of time. That rapid final stage is what separates a true gas giant from a merely large rocky world. Not a different mixture to draw on, but a solid seed that grew just large enough, just early enough, to catch the surrounding gas before it thinned away and vanished for good. Farther out still, Uranus and Neptune tell a slightly different version of the same story. Both carry a noticeably larger share of ice relative to gas than Jupiter or Saturn do, their outer layers thinner and their interiors weighted more heavily toward frozen material than toward captured hydrogen and helium. The likeliest explanation is timing rather than any difference in local recipe. Their solid seeds, forming farther from the Sun, where material generally gathers more slowly, appear to have reached the size needed to start pulling in gas only once most of the surrounding gas nearby had already thinned and drifted away. They arrived at the right stage of growth. In other words, a little too late for the gas still to be waiting for them in any great quantity. Both worlds remain far less thoroughly studied than their larger neighbors, and much of what is known about their interiors still rests on models and not on direct measurement. What they gathered instead, in far greater proportion, was the ice their own neighborhood had always had in generous supply. Every one of the largest worlds in the system carries its own small collection of what are usually called regular moons, and the family looks strikingly similar from one giant to the next. These moons circle close to their planet's own equator instead of at some random tilt, follow orbits that are close to perfectly circular instead of markedly stretched, and travel in the same direction their planet spins. all lined up together like a small, neat formation, instead of a scattered handful of unrelated wanderers. That kind of orderly arrangement rarely happens by chance. Random capture, one object caught here and another there over a long stretch of time, tends to produce exactly the opposite. A messy scatter of tilts, directions, and distances with no shared pattern at all. A well-ordered family like this points instead toward a shared, orderly process of formation. The same process for every moon in the group, all at once. That orderly process turns out to echo in miniature the very story already described at a much larger scale. Around each growing giant, while it was still gathering its own envelope of gas, a smaller disk of leftover material appears to have formed and settled into its own thin, flat plane, circling the young planet much the way the young sun's own disk once circled the young sun. Within that miniature disk, small grains gathered into pebbles, pebbles into moonlets, and moonlets eventually into the well-behaved family of regular moons still ringing that planet tonight. The comparison is not exact in every detail, since a young planet's own disk is far smaller and shorter-lived than the sun's. But the underlying pattern of assembly matches closely enough to be worth noting. One recipe tried twice at two very different scales. Once around the sun, producing the 8 planets and everything else already described. And once again around each giant, producing its own small system of orderly moons in exactly the same pattern. Look closely at the composition of moons within Jupiter's own family of 4 large moons, and a familiar gradient reappears. The very same one the frost line produced across the whole system, only much smaller. Io and Europa, closer in, are dense and rocky, built mostly from rock and metal instead of ice. Ganymede and Callisto, farther out, are noticeably lighter and richer in ice, holding a much larger share of frozen material relative to rock. The pattern is clearest here at Jupiter, where the density figures line up neatly with distance from the planet. Around Saturn and Uranus, the same sorting appears to have happened too. But later heating and mixing inside those icy moons has since blurred the neat density trend that Jupiter's family still preserves so clearly. Alongside that neat, orderly family, every one of the giants also carries a second, much messier group. Moons on distant, tilted, often backward orbits, scattered at odd angles instead of lined up neatly along their planet's equator. These do not fit the orderly pattern of formation described a moment ago at all, and researchers generally do not think they formed there in the first place. The leading explanation instead is capture. Small bodies that were originally traveling their own independent path through the outer system, wandering too close to a giant's gravity at some point, and getting pulled permanently into orbit rather than continuing on their way. Once captured, an orbit like this tends to stay stable for an extremely long stretch of time. So a moon caught this way early in the system's history can remain in place for a very long stretch of it afterwards. Unlike their well-behaved neighbors, these captured moons carry no shared pattern of tilt or direction at all, each one instead recording its own separate, accidental arrival. A stranger folded quietly into a family it was never originally born into. Stand back now, from the small, pale grains that formed first, all the way out to the giants and their families of moons, and one plain shape holds all of it together. Every rock examined, every layer of metal and stone inside the 4 inner worlds, every stretch of frozen material sitting patiently beyond the frost line, and every trace of captured gas wrapped around the giants, all trace back to one original mixture, sorted afterwards by distance from the center and by how much time each patch of material had before the surrounding gas thinned away for good. Rock, metal, ice, and gas are not four separate stories. They are one story, told 4 times, at 4 different distances, from a single mixture that never had to be anything other than itself to end up this varied. That is the shape the whole system settled into. Not a question left hanging, but a shape completed, holding steady for whatever lies beyond it. Beyond Neptune, the neat sorting that shaped everything else in this system runs out of steam. Out there sits a shipment of raw material that never got claimed by anything larger, never got folded into a planet, and never got used up. For most of recorded astronomy, the last planet looked like the edge of everything, and nobody suspected otherwise. That assumption held until the early 1990s, when the first faint object past Neptune finally turned up in an ordinary research telescope, never built with that search in mind. A single point of light rewrote the map that night. What lies past Neptune is no empty boundary at all, but a wide, cold storeroom stocked with the same raw ingredients used everywhere else in this system. Left standing because both time and material ran short before anything larger could be built from them. Mapping exactly how far that shipment actually reaches has taken decades of patient, incremental searching, one faint point of light at a time. From here, the question changes shape. Not what got made, but what got left over. That storeroom has a name, the Kuiper Belt, a broad, flattened ring of icy bodies circling far beyond the last planet. Nobody confirmed it was there until 1992, when astronomers scanning the dark space past Neptune finally caught a single small object moving against the fixed stars, even though a handful of researchers had already argued on paper from the flat, low-tilt orbits of the short-period comets that such a belt ought to exist. One small, slow-moving dot changed that overnight, and within a few years, dozens more turned up, then hundreds, then thousands, each one confirming that the earlier guess had been more than a hunch. The belt itself stretches across a vast ring of space, thin compared with its width, but enormous compared with anything closer to the Sun, and every fresh survey conducted since then has added more names to the list, filling in a steadily crowded, cold neighborhood that had gone unnoticed for most of astronomy's history. Counting everybody large enough to matter, the region holds a whole population that took decades of careful searching to bring fully into view, long after the first theorists argued it had to be there. By weight, the Kuiper Belt is a disappointment to anyone building a model of how it formed. Add up every known object out there, and the whole belt still comes in far lighter than the simulations expect, sometimes by 90% or more. Something clearly gathered less material than the early sums predicted, or something later carried much of it away. Neither answer is settled. A region this wide, at this distance from the Sun, should, in theory, have gathered enough solid material to build several planets the size of Earth. Instead, what remains looks more like the crumbs left on a table after most of a meal has been cleared, rather than the meal itself. That missing mass is not a small rounding error either. Models built around a normal-sized belt fail to match what telescopes actually count out there. Whatever happened out there, the belt keeps a memory of its own incompleteness, written directly into its mass. A shortfall no single object, however carefully studied, can explain on its own. Pluto sits inside this same belt as one ordinary resident among thousands, not as some exception that slipped through the rules by accident. Its size once seemed to set it apart, back when it stood alone as the 9th planet on classroom charts. But every later discovery in the same region chipped away at that separation. Its makeup matches its neighbors closely. A mix of rock and frozen gases, built from the identical raw material that fills the remainder of the belt around it. Its orbit carries the same rhythm many of its neighbors share, locked into step with Neptune rather than moving freely. None of that makes Pluto lesser. It simply means the label attached to it in 1930 said more about the state of the search back then than about Pluto's actual place among its neighbors. Modern classification schemes now group Pluto with its true neighbors, instead of treating it as a category of one, a shift many textbooks still struggle to keep pace with. A member of a large, quiet family, not a lone outsider standing apart from everyone else in the belt. A large share of Kuiper Belt objects, Pluto included, complete exactly 2 trips around the Sun in the time Neptune completes 3, a regular ratio that does not appear in nature by pure chance. Bodies caught in this rhythm never drift close enough to Neptune for its gravity to fling them away, even though their paths cross Neptune's own orbit again and again over the centuries, kept apart at every crossing like 2 dancers who never collide because their steps always land at slightly different moments. Thousands of objects share this exact ratio, spread across a huge stretch of the belt, keeping the identical rhythm independently of one another, and astronomers gave this particular group a name of its own. A coincidence this precise, repeated this many times, is really no coincidence at all. That shared rhythm is a record, written in orbits instead of ink. Neptune, astronomers now think, was not always where it sits today. It worked its way further out from the Sun, sometime after the planets first formed, sweeping up nearby material and carrying some of it along for the ride, so that objects caught early in that sweep settled into the same steady ratio Neptune itself was passing through at the time. No spacecraft watched this happen, and no photograph exists of the process in progress. But what survives instead is the pattern. Thousands of bodies still keeping time with a planet that finished moving long before humans built the instruments needed to notice. And working backward from how tightly that ratio holds today, researchers can even estimate roughly how far and how gradually that outward journey must have unfolded. A slow shuffle, frozen mid-step, and never undone. Not every part of the belt got swept up into that migration story. A separate population, called the cold classicals, sits further out on orbits that are close to circular and barely tilted at all, tracing gentle, undisturbed loops that look almost untouched by anything since they first settled there. Their orbits show none of the scars that gravitational encounters tend to leave behind. No sudden tilts, no stretched out ellipses, no sign of ever having been pushed around by a passing planet. Records that would show up clearly if any large body had ever crossed paths with them since the belt first settled into its current shape. Because of that calm history, many researchers treat this population as the single most pristine sample of outer solar system material known to exist, a leftover shelf that nothing ever came along to disturb. Colors vary across this group in ways that hint at real chemical differences and not accidents of lighting. Differences that may map onto exactly where, out of the original mixture, each body first came together. Several proposed sample return missions have named this population as a prime target, precisely because nothing else nearby has stayed this quiet for quite this long. Undisturbed in this part of the sky is not the same as uninteresting. Arrokoth offers the closest look anyone has ever had at how these bodies actually came together. A distant spacecraft flew past it and returned images of 2 separate lobes, gently pressed against one another along a shared, flattened seam, rather than fused by any violent collision. Nothing about its shape suggests speed. The 2 pieces line up neatly, their long axes matching, the way 2 soft objects settle together when they drift into contact at walking pace, not crashing. Had they come together quickly, the impact would have left crumpled edges, scattered debris, or a jumbled asymmetric shape, not this calm, mirrored pairing. Instead, Arrokoth reads like a slow handshake, preserved in ice for billions of years, undisturbed since the moment it happened. Nothing in the images shows the fractures or debris fields that a faster, more violent merger would have left scattered across its surface. One frozen snapshot of construction, still holding its original pose out at the edge of the mapped solar system. Not everybody born in that same region stayed on a well-behaved orbit. Close encounters with Neptune, spread out across billions of years, have flung a large population onto stretched, tilted paths that swing wildly between the inner edge of the belt and far beyond it, a group astronomers call the scattered disk. Some swing in almost close enough to cross Neptune's own path before racing back out to enormous distances, taking centuries to complete a single loop and sweeping out enormous volumes of space in the process. None of them behave like members of a stable family anymore. What holds this group together is not a shared orbit at all, but a shared history of having been pushed, each one thrown from roughly the same starting shelf by roughly the same planetary hand. A handful of bodies in this same outer region grew large enough and round enough to earn the label dwarf planet alongside Pluto. Ceres, circling the Sun on a wide, tilted path and matching Pluto closely enough in size that its discovery helped trigger the whole debate over what deserves the word planet at all. Makemake, keeping to a much steadier orbit with an unusually bright, faintly reddish surface that hints at a chemistry slightly different from its neighbors. And Haumea, spinning so quickly that its own rotation has stretched it into a squashed, elongated shape and not a smooth sphere, completing a full spin in only a few hours. Each of these three carries a different oddity, likely traced back to whatever specific encounter or collision shaped that particular body during its own crowded youth. And none of the three shares an orbit closely enough with the others to suggest a common recent history beyond the raw material they were all built from. Same family, three separate stories. Head far enough out, and the Kuiper Belt does not fade away gradually. It stops, or seems to, along a fairly sharp line where the number of known objects drops off far faster than anyone expected. Some call this the belt's outer cliff, a term that captures how abrupt the fall-off looks on paper once the numbers are plotted against distance. A handful of explanations compete for the honor of solving it. Perhaps material out there is real, but too faint and scattered for current telescopes to catch reliably. Or perhaps something long ago genuinely swept that stretch of space clear of anything sizable. Neither idea has won the argument outright. The edge itself might mark where the original supply of building material ran out completely, and not where anything came along afterward to clear it away. Future telescopes with sharper vision may eventually settle the argument by counting fainter, more distant objects that current instruments still cannot pick out reliably. A boundary that raises more questions than it settles. Pull back far enough, and the shape of the whole region comes into focus. Nothing sits past Neptune by accident, and nothing sits there because it failed at being a planet. It sits there because that particular shelf of the original mixture never received the density, the warmth, or the time needed to be pulled into anything larger. Every resonance, every scattered orbit, every oddly shaped dwarf planet out there is a fragment of the same unfinished project, still holding roughly the shape it had the day the building stopped. Call it a border if that helps picture it, but it reads more like an inventory left exactly where the workers set it down. Whatever finally explains its outer edge, the belt as a whole keeps behaving like unfinished business, not a finished closing chapter. The far edge of the planets is less a wall than a warehouse, still stocked, still cold, and still waiting. A comet is that same unclaimed shipment, only kept colder and further from disturbance than almost anything else within reach. Most of the solid bodies closer to the Sun have been baked, melted, crushed, or reshaped at least once since they first formed. Comets, for the most part, have not. Whatever ices and dust first came together to build one of these bodies have mostly just sat there since, barely warmed, barely touched, and rarely disturbed by anything more violent than the occasional gentle nudge from a passing planet's gravity, and even the handful that do pass close enough to warm noticeably keep the bulk of their material locked safely inside. That makes a comet less like a fossil and more like an unopened package, and spacecraft that have flown close enough to study one directly are, in effect, opening the least altered parcel this system has ever kept sealed shut. One particular comet, known by the short label 67P, got studied close up by a spacecraft that matched its speed and rode alongside it for 2 full years instead of just flying past. What that mission found was a nucleus shaped like 2 lumpy sections joined at a narrow neck, darker across its whole surface than a lump of coal, and less dense overall than an equal volume of plain water. Under a telescope from a distance, that darkness and shape had suggested something solid and heavy. Up close, the comet turned out to be closer to a loose, fragile pile than a single hard rock. A rubble heap of ice and dust barely held together by its own weak gravity, riddled with gaps and pockets instead of packed tight all the way through. Scientists studying the images still debate exactly how such a fragile pile ever held together long enough to survive billions of years of drifting. Fragile, porous, ancient, and, against every instinct, remarkably light for its size. That same spacecraft measured the ratio of ordinary hydrogen to its heavier cousin locked inside the comet's water ice. A ratio that works almost like a fingerprint for wherever the ice first formed. Earth's oceans carry their own version of that ratio, one scientists have measured with great precision over many decades of careful sampling, refining the number generation after generation as instruments grew steadily more sensitive. When the 2 numbers were finally compared side by side, they did not match. That single mismatch reopened a question many researchers had assumed was mostly settled. Whether comets like this one delivered a meaningful share of Earth's water in the first place, or whether the water arrived by some other route entirely. Other comets, measured since, have shown ratios that land closer to Earth's own, muddying the picture instead of clearing it up. A handful of comets, sampled from the population closer to Neptune, have shown ratios noticeably closer to Earth's, hinting the answer may involve more than one single source. One number, checked twice, and an old answer stopped looking quite so certain overnight. A separate spacecraft, sent to collect dust instead of riding alongside a comet, flew close enough to a different one to catch particles streaming off it in a fine collector and carry them home for study on Earth. Inside that collected dust, researchers found tiny mineral grains that, as far as anyone can tell, only form under intense heat, the kind found close to a young star, rather than out in the cold reaches where comets are built. A cold, icy body, born in one of the coldest corners of the whole system, was carrying material forged much closer to the center of it. That single discovery argued for something long suspected, but never directly confirmed. Raw material moved across enormous distances before anything finished settling into its final place. Heat from the middle, ice from the edge, mixed together inside one small, frozen traveler. Comet ice is rarely just frozen water and nothing else. Spacecraft and telescopes studying these bodies have picked out water, carbon dioxide, carbon monoxide, ammonia, and methanol among the frozen ingredients, layered together instead of sitting in separate pockets, mixed in with more complicated molecules built around carbon and nitrogen, the same two elements that sit at the center of most of the chemistry Earth's own biology eventually put to use. None of this means anything alive rode along inside one of these bodies. It means the raw chemical vocabulary needed for that kind of chemistry existed scattered through the cold outer reaches of the young system, folded into ice long before any planet had a surface capable of hosting it, with different comets showing slightly different proportions of these same ingredients. A frozen chemistry set, carried far from the workshop that first stocked it. On that same close encounter with 67P, instruments detected the simplest amino acid known, along with a trace of phosphorus, both locked into the material streaming off the comet's outer layers. Amino acids are the building blocks biology uses to construct proteins. Phosphorus, meanwhile, sits at the center of the molecule that carries genetic information in every living thing on Earth. Finding both inside a comet is not evidence of life out there, and no scientist studying the results claimed otherwise. It is evidence of ingredients, raw chemical pieces present in the material long before any planet existed to make use of them. The mixture that built this whole system was clearly carrying more of a chemical toolkit than anyone expected from something so cold and so far from the sun. Laboratory experiments since then have shown that similar molecules can form easily under the cold, radiation-exposed conditions typical of comet ice. Nothing unusual needs to trigger them. Useful pieces scattered generously, with no guarantee any of them would ever get picked up. Comets split cleanly into two broad families once their orbits get tracked over time. One family swings past the Sun on a fairly tight, repeatable schedule, returning every few years or decades from a source that sits not far past Neptune, in roughly the same neighborhood as the icy ring circling out there. The other family arrives from somewhere far more distant, on a path so wide that a single visit might be the only one that particular comet ever makes within recorded human history. These wide-swinging visitors approach from every direction in the sky rather than one shared plane, unlike their tighter orbiting relatives. That difference in behavior points to two very different storage shelves out past the planets, one considerably closer than the other. Astronomers can often tell which family a newly spotted comet belongs to within days, just from the shape and tilt of its orbit alone. Two families, two very different journeys home, and only one of the two keeps a schedule anybody could set a calendar by. The far visitors trace back to a reservoir known as the Oort cloud, an origin that seems almost to contradict itself. Material formed much closer in, among the growing giant planets, only to be thrown much farther out by the very same planets that helped build it. Rather than condensing peacefully at some enormous distance from the Sun, these bodies most likely started out mixed in with the remainder of the planet-building material, closer to where the giants themselves were assembling. As those giants grew heavier, their gravity began flinging nearby debris outward with tremendous force, some of it escaping to distances that dwarf anything else in this system. What looks today like the most remote material belonging to the Sun did not form remote at all. Built in a crowded, busy neighborhood among growing giants, then thrown outward by the very gravity that helped finish assembling them. That process of ejection likely played out many times over, across the busy early years when the giant planets were still finishing their own construction. Remote by expulsion, not by birth. Put those two comet families and their two different homes together, and an odd symmetry appears. The farthest material belonging to the Sun, flung out to distances that make even the outer planets look close by comparison, is built from essentially the same mixture as the nearest, most familiar ice, sitting far closer to home. Distance did not change the ingredients, it only changed the address. A comet arriving from the most distant reaches ever measured carries water, dust, and organic molecules that would not look out of place inside a comet born much nearer the planets. And chemical analysis run on comets from both families keeps turning up the same handful of core ingredients, however different the two journeys home actually were. What separates the near visitor from the far one has nothing to do with what either one is made of, and everything to do with how forcefully it got thrown and how long ago the throw happened. Same pantry, two very different shelves. Ice held this steady, this far from any warmth, keeps a kind of memory that rock rarely manages. Every comet examined closely so far has told a version of the same story. Raw material from the earliest mixture, barely rearranged, occasionally interrupted by a brief blazing pass near the Sun before heading back out to the cold. Nothing about a comet was ever finished into something larger, and that failure to finish is exactly what makes it worth studying now. Each close pass near the Sun costs a comet a little of its original material, meaning even this frozen archive is slowly, gradually running down. What melts briefly into a glowing tail every few years or decades is not decoration, but the least altered surviving sample of the original mixture, unlocked briefly each time gravity swings it close enough to the Sun to let a little of it show. Past the frost line, ice stops being decoration and becomes a proper building material, sitting alongside rock instead of melting away from it. Many of the large moons circling the outer planets are built from roughly equal parts of both, layered together the way a cake alternates between different textures. For some of these moons, ice alone accounts for close to half of the total mass, an amount that would be unthinkable for anything orbiting much closer to the Sun. That balance shapes almost everything else about how a moon like this behaves. Its density, its color, how easily its crust deforms, even how it holds heat. Differences that show up clearly the moment two moons of similar size are compared side by side. Rock alone could never have built a body this size out here. There was not enough of it available at this distance. Compare two moons built at similar distances, and the one carrying more ice will almost always turn out lighter overall, however similar the two look from a distance. Ice filled in the remainder of the recipe, quietly doing half the construction work. Ganymede and Callisto, two of the largest moons circling the giant planet nearby, are close enough in size and close enough in origin that early observers assumed they must be built the same way inside. And yet they are not. Ganymede separated cleanly at some point in its history, rock sinking toward the center while ice rose toward the outside, leaving distinct layers behind, while Callisto shows almost none of that same separation. Rock and ice still mixed together through most of its interior. Both moons started from a similar supply of material at a similar distance from their planet, which makes the difference between them one of the harder puzzles left in this part of the system. Something about their early histories Perhaps how quickly each one came together, pushed one toward well-ordered layers, and left the other essentially unsorted. And no single explanation has convinced every researcher studying the pair. One planet, one starting supply, and two moons that finished the job in opposite ways. The thick, hazy atmosphere wrapped around Titan, the largest moon out here, is mostly nitrogen, a gas that seems like an odd choice for something built this far from the sun. The likeliest explanation traces that nitrogen back to ammonia ice, delivered frozen solid during the moon's construction and only broken apart afterward, its nitrogen slowly released while its hydrogen escaped or bonded elsewhere into other compounds. Sunlight this week could not easily manage that chemistry alone, so something else, whether early heat left over from the moon's own formation or steady bombardment by charged particles, likely finished the job over a very long stretch of time. What breathes around Titan today began as a solid frozen mineral rather than a gas, unlocked slowly, not arriving ready-made. Similar chemistry, running more slowly or incompletely, may also explain the thinner traces of nitrogen turning up on a handful of other icy worlds studied since. An atmosphere built out of ice, one patient chemical step at a time. A much smaller moon, Enceladus, sprays a fine mist of ice and vapor out through cracks near one of its poles. A plume caught directly by a passing spacecraft that flew straight through it to sample the material firsthand. Mixed into that spray were salts, the same kind that dissolve out of rock when water sits in long contact with it, along with extremely fine grains of silica so small that only a particular kind of chemistry, involving warm water meeting rock under real pressure, seems able to produce them. Neither ingredient forms on its own inside plain ice sitting quietly in the cold. Both point toward liquid water somewhere inside this small moon, in direct contact with a rocky interior, rather than ice simply melting near its crust. Later flybys measured the composition of that spray in even finer detail, confirming the same salts and grains turning up consistently, flyby after flyby. A small moon, spraying evidence of its own inner chemistry into open space for any passing spacecraft willing to fly straight through it. Europa, one of the large moons circling the next planet inward from here, wears a crust of solid ice thick enough by most estimates to bury a mountain range completely beneath it. From orbit, that crust looks smooth compared with most rocky worlds, crisscrossed by long, reddish-brown streaks rather than deep craters, as though something beneath keeps slowly resurfacing it and erasing older scars. Chemists studying the color of those streaks have found sulfur and salt compounds embedded in the ice, chemistry that does not simply appear out of nowhere in a block of frozen water sitting still. Something below keeps feeding material up into that crust, cracking it, staining it, and occasionally resurfacing it, over timescales far shorter than the moon's own age. Crater counts across that same crust show it has been resurfaced far more recently than the moon itself first formed, treating the surface almost like a slowly updating record. The ice on top is not a sealed lid, but a bulletin board, scratched and restocked from below far faster than plain ice this cold has any right to change. Triton, the largest moon circling the outermost planet, does not match its planet's other companions in composition, size, or history. Its surface chemistry lines up far more closely with material sampled from the icy bodies drifting in the distant belt beyond Neptune than with anything else found closer to that planet, right down to the mix of nitrogen and methane ice coating its crust. Its orbit carries a shape and tilt that set it apart from every other sizable moon nearby, behavior that fits poorly with the idea that it grew up alongside its planet from the same disk of local debris. The likeliest story is Capture, a body built somewhere else entirely, out among the icy population past Neptune, that ended up bound to a planet it had no part in building. Simulations of that capture event suggest the process would have violently reshaped much of the planet's original moon system as it happened. A native of one neighborhood, still carrying its old chemistry, now locked into orbit around a planet it never grew up beside. At the temperatures found this far from the sun, water ice stops behaving like the fragile, slippery stuff found in a household freezer and starts behaving structurally more like solid rock. It holds its shape under pressure rather than slumping, cracks along clean lines instead of crumbling into powder, and, given enough time and enough gentle stress, can even flow very slowly, the way rock deep inside a planet flows under its own weight over millions of years. That single property is the reason so many of these icy moons show real geological features at all: ridges, cliffs, long cracks and slow flows, rather than featureless, dead grey balls hanging in the dark. And engineers designing future landers have had to treat the ground on several of these moons more like solid stone than like ordinary ice. Cold enough, ice stops behaving like mere decoration and becomes architecture, holding up cliffs and canyons the same patient way stone does everywhere else. Count up every outer moon where evidence now points toward a hidden layer of liquid sitting beneath a shell of ice, and the number climbs well past just one or two special cases. Several separate moons, orbiting two different giant planets, now show independent signs, whether in their magnetic behavior, their crust cracking, or the material sprayed directly out into space, that a real layer of liquid persists somewhere beneath their frozen shells. That would have sounded absurd only a few decades ago, when a moon this far from the sun's warmth was assumed to be frozen solid from crust to core without exception. Instead, several of them appear to be keeping something moving and unfrozen deep inside, hidden under a lid of ice thick enough to make direct study nearly impossible from orbit alone. Each new mission sent to study one of these moons closely tends to add fresh evidence to that same growing list, instead of removing any names from it. Frozen on the outside is turning out to be a poor guide to what waits underneath. None of that hidden warmth traces back to sunlight, which arrives this far from the sun, far too weak to melt anything at all. The real source is mechanical rather than solar, as each of these moons follows its own slightly stretched orbit around its planet. The planet's gravity squeezes and releases it slightly with every pass, flexing its interior the way repeatedly bending a piece of wire eventually warms it in a hand. That flexing happens over and over, orbit after orbit, for as long as the moon's path stays even a little uneven and not perfectly circular. Neighboring moons often help keep that path uneven by tugging on it gravitationally in a steady, repeating rhythm, refusing to let the orbit settle into the calm circle it would otherwise loosen into. The strength of that squeeze depends heavily on exactly how stretched the orbit is, which is why some moons stay warm inside while very similar neighbors stay frozen solid. Warmth, out here, comes from being gently squeezed, not from being lit. Put the ice, the cracks, the plumes, and the hidden warmth together, and the wet half of the original mixture turns out to have survived rather well, just in a very different form than it took closer to the sun. None of it stayed as open water exposed to the sky, the way it briefly might have on a young rocky world, evaporating or freezing solid within a geological eye blink instead of lingering. All of it now sits locked beneath solid shells, kept liquid not by warmth from outside, but by the steady mechanical squeeze of neighboring gravity. The far side of the frost line did not simply freeze solid and stop changing the moment it formed. It kept working quietly, moon by moon, long after everything else in the system had mostly settled down. Warmth generated this way can persist for as long as the orbital rhythm driving it holds steady, potentially for the entire remaining lifetime of the system. Cold on the crust, restless just beneath it. Somewhere in the middle of the growth story that built every solid body in this system, the standard explanation runs into real trouble. Once dust has clumped into pebbles roughly the size of a stone a person could hold, the models predict two problems happening at once. Gas drag should drain their orbital energy fast enough to pull them spiraling inward long before they finish growing, and collisions between pebbles this size should shatter as many as they build. Neither problem is fatal on its own. Together, they leave a genuine gap in the story, a size range where growth ought to stall out almost as fast as it begins. Nobody disputes that planets eventually formed anyway. The disagreement sits entirely in the mechanism, not in the outcome. Laboratory experiments have reproduced the shattering directly, and the inward drift falls straight out of the equations, confirming the problem is real rather than just a flaw in the modeling. What remains disputed is exactly how construction managed to slip past this particular stretch of the process without losing most of its raw material along the way. The leading answer to that gap goes by the name streaming instability, clumps of pebbles concentrating themselves densely enough in the right pocket of gas to collapse under their own gravity straight into a body large enough to skip the danger zone entirely. Once that first sizable body exists, a second process called pebble accretion takes over the growth from there, letting it pull in the surrounding smaller pebbles gently through gas drag, gathering them almost continuously instead of through rare, violent impacts. That steady collection can add mass far faster than collision-by-collision growth ever could, letting a body grow into a full planetary core in a fraction of the time older models required. Several details of exactly how efficiently both steps work in practice remain unsettled. Observations of young stars elsewhere, still surrounded by their own visible disks of gas and pebbles, offer indirect support for this same two-step process happening in real time. Not the final word on the story, but for now, the best patch anyone has found for a genuine hole in it. Return for a moment to the same tiny, once-molten beads of rock described earlier, scattered inside so many of the oldest meteorites ever studied, and the puzzle they represent has still not been solved. Candidates for that heat source keep circulating through the scientific literature, shock waves rippling through the gas, lightning-like discharges triggered by friction between grains, or brief flashes tied to the earliest growing bodies nearby. None of these candidates has gathered enough supporting evidence to close the case outright, and each one struggles to explain why the beads turn up in such enormous numbers instead of as rare, isolated events. Whatever the true trigger eventually proves to be, it had to operate briefly, repeatedly, and across an enormous stretch of the young system to leave behind quite this many beads. Billions of these tiny beads exist across countless meteorites, each one a separate small record of a heating event nobody has yet managed to identify with any certainty. For decades, the best measurements of the Sun's own outer layers have refused to agree with the best models of its interior, and nobody has fully closed the gap. Spectroscopy of the faint outer layer, where sunlight actually escapes, gives one answer for how much oxygen, carbon, and other heavier elements the Sun carries. A separate method, listening to sound waves rippling through the entire body to map what lies beneath that visible layer, keeps demanding a somewhat higher figure to make the internal structure add up correctly. Neither side has found an obvious flaw in the other's technique. Proposed fixes range from revised atomic physics, governing how that outer layer absorbs and releases light, to the idea that heavier material has slowly settled deeper into the Sun than current models assume. The disagreement is not large in absolute terms, only a matter of 1% or 2%, but it sits at the very foundation of how every other star in the sky eventually gets measured. A gap small enough to overlook and stubborn enough that nobody has yet made it disappear. Whether the giant planets formed roughly where they orbit today or traveled considerably from their original starting points before settling into their current positions remains one of the more contested questions in the whole field. The resonance patterns carved into the belt past Neptune argue strongly for real movement at some point, a kind of fossil record written into thousands of separate orbits. Exactly how far each giant traveled, in which order, and over what stretch of time, is where agreement breaks down. Different research groups, running different versions of the calculation, arrive at noticeably different answers, some involving a fairly gentle outward crawl, and others involving a much more dramatic rearrangement early on, disagreements that trace back less to bad data than to how each model chooses to weigh the same handful of orbital clues. All of the leading versions agree that some amount of movement happened. Each new simulation run, with slightly different starting assumptions, tends to produce a slightly different outcome, which is part of why the argument has proven so difficult to close. None of them agree yet on the details, and the debate shows no sign of settling soon. Something also kept 2 separate chemical signatures found across different meteorites from blending together for several million years, even while everything around them was still swirling and colliding in the same crowded disk of material. The leading explanation points to Jupiter, or rather, to whatever body was growing into Jupiter's position at the time, reaching a large enough size early enough to carve a physical gap in the surrounding material. A gap that size could act like a wall, letting very little material cross from one side to the other, while both regions kept evolving mostly on their own, developing subtly different chemistries, even though both sides started from the same original supply. Direct evidence for that wall does not exist. Nobody watched it form. What exists instead is a stubborn difference in composition on either side of where that wall should have stood, still measurable in meteorites collected and studied today. Meteorites collected from opposite sides of that presumed boundary keep confirming the split decades after it was first proposed, even without any direct picture of the barrier itself. A silent divider, argued for entirely by its aftermath. A small handful of bodies found drifting far beyond the belt's wandering, scattered population refuse to fit cleanly into either of the usual categories. They swing in closer to the Sun than anything belonging to the most distant storage shelf ever should. Yet at their farthest point, they travel out to distances too extreme for Neptune's gravity to have thrown them there directly. Sedna is the best-known example, tracing an orbit so wide and so stretched that a single loop takes many thousands of years to complete. And something had to push these bodies onto such an unusual path. Whether an unseen planet still undiscovered, a passing star sometime in the ancient past, or a process nobody has proposed yet, none of which commands wide agreement. A small number of additional objects, discovered since Sedna itself, appear to share a similarly stretched, isolated orbit, sitting in a gap between 2 shelves and matching neither one convincingly. Nobody watched the gas around the young Sun disappear in real time. The only direct evidence for how quickly that happened comes from watching other young stars instead. Telescopes surveying stellar nurseries elsewhere in the galaxy have tracked hundreds of young stars still wrapped in their own disks of leftover gas and dust. checking cluster after cluster of different ages to see at what age the gas is usually already gone. Across that whole survey, the gas tends to vanish within a handful of million years on average, sometimes faster, rarely much slower. Applying that same average timeline to the young sun gives researchers their best estimate for how long any growing planet here had before the raw material for building an atmosphere ran out completely. Some of the youngest systems surveyed still show plenty of leftover gas, while older ones nearby have lost theirs entirely, bracketing the typical timeline from both directions at once. An estimate borrowed from strangers rather than measured directly at home. And yet, it sets the deadline behind almost everything else in this story. Add together every measured object drifting through each of the outer storage shelves covered here, from the belt past Neptune to the far edges where lone wanderers turn up, and the total still falls dramatically short of what construction models say should have been available out there originally. Estimates for the missing amount vary, but several independent calculations land on a shortfall of 90% or more, an amount far beyond what simple undercounting by faint, hard-to-spot objects could ever explain. Some of that material likely got flung entirely out of the system by gravitational encounters over billions of years, joining wanderers that will never return, drifting now through interstellar space far beyond any telescope's practical reach. Some of it may have been ground down into dust too fine to track directly by any survey. Nobody has an accounting that closes the books completely. Comparing several independent surveys run by different teams using different telescopes keeps producing roughly the same shortfall, which argues against simple measurement error as the explanation. A construction site with most of its delivered material unaccounted for on the final inventory. None of this uncertainty makes the whole mixture and sorting story wrong. It makes it unfinished, the way most genuine scientific explanations stay unfinished, for as long as anyone keeps looking closely enough to notice the gaps. Every open question raised in this block is a place where the data runs out before the explanation does, not a place where the whole idea collapses. Chondrules still puzzle researchers. The size gap in growing pebbles still needs patching. Isotopic walls missing mass. Oddly placed wanderers. None of them have easy final answers yet. What holds steady underneath every open question is the mixture itself. The same raw material keeps turning up, checked and rechecked, in body after body, no matter how far out the search reaches. Each of these open questions gets revisited every time a new spacecraft, telescope, or sample return mission adds fresh data to the pile. Unsettled in the details, settled at the foundation. The delivery that built this whole system never fully stopped. It only slowed to something almost too quiet to notice. Earth alone gathers something on the order of several thousand tons of fine dust from space every single year, arriving as countless microscopic grains too small to burn up visibly or ever register to anyone standing on the ground, drifting down silently and settling onto rooftops, snowfields, and ocean floors without a single flash of light announcing their arrival. Researchers have learned to collect and count them anyway, sorting them out from ordinary terrestrial dust by their distinct chemistry and shape. Using specialized collectors, some flown on high-altitude aircraft and others buried in Antarctic ice, built specifically to catch a portion of that quiet, constant rain. A shipment that started billions of years ago is, technically, still being unloaded, one grain at a time, every single night. Bringing either of those two asteroid samples home took engineering built entirely around a single goal: keep the material from ever touching Earth's air, water, or dust before scientists could study it inside a controlled laboratory. Both containers stayed mechanically sealed from the moment of collection until they reached dedicated clean rooms years later, opened only under carefully monitored conditions designed specifically for material this fragile. That level of care matters enormously, because almost every meteorite that falls to the ground gets changed a little by the landing itself and by the years spent sitting exposed afterward. Engineers on both missions worked out those sealing systems years in advance, anticipating exactly how easily ordinary contact with Earth's own air could compromise material this old. A portion of each sample was deliberately set aside, still sealed, for scientists working decades from now with instruments that do not exist yet. What eventually reached the laboratory was as close to the moment of collection as any sample returned to Earth has ever been. Inside both of those carefully sealed samples, researchers found clay minerals, the kind that only form when liquid water sits in long, patient contact with rock, along with a wide range of organic molecules built around carbon. Neither material had ever been heated significantly since it first came together, which means both records survived essentially unedited across the full span of the system's history. Water once moved through that rock, slowly, reshaping its minerals from the inside without ever needing to be a river or an ocean, just patient contact held over a very long stretch of time. Carbon-based molecules sat alongside that reshaped rock the whole time, neither destroyed nor transformed by any later heating event. Laboratories around the world have since requested small portions of both samples, comparing results independently to make sure no single team's methods biased the conclusions being drawn. Two small, dark rocks, handled with extraordinary care, turned out to be carrying some of the clearest record of water rock chemistry ever recovered from anywhere in this system. Nothing about this system finished moving once the planets settled into roughly their current positions. Orbits still shift by tiny amounts with every passing century, nudged gently by the combined gravity of every other body sharing the same neighborhood. Weak spots inside asteroids and comets still fail under stress now and again. The breaks send larger bodies splitting into smaller fragments that then follow entirely new paths of their own. Dust generated by those breakups keeps drifting slowly inward under gentle pressure from sunlight, eventually joining the same quiet delivery, arriving at Earth and every other planet nearby. None of this happens quickly enough to notice within a single human lifetime. None of these changes threaten the overall architecture built long ago. They simply keep sanding down its rougher edges a little further with each passing century. The construction crew did not so much finish the job as set down its tools and slow to an almost imperceptible pace, leaving the site technically still active. That same isotopic split shows up in every large collection of meteorites studied today, not just in the handful of specimens that first revealed it decades ago. A fragment carrying the signature of material assembled closer to the Sun essentially never turns up, mixed in with one carrying the signature from farther out, even after 4.5 billion years of stirring, colliding, and drifting across the whole system. A single fragment, tested in a laboratory today, can usually be assigned to its side of that early boundary with real confidence, based on nothing more than its chemistry. Museums and laboratories worldwide keep adding freshly catalogued meteorites to the record, and the split holds up again with almost every new addition. That kind of persistence, across thousands of separate specimens and decades of independent testing, is what convinces most researchers the separation reaches deep into the material itself, instead of sitting only on its surface. Two isotopic signatures still holding apart long after the boundary between them stopped being enforced by anything but chemistry. Strip away every individual object covered across comets, moons, belts, and unresolved puzzles, and one claim holds up better than almost any other made tonight. Almost nothing here was ever carried in from outside this system, at least not in any amount large enough to matter after its material first came together. Every atom in every rock, every particle of ice, every streak of color on every crust traces back to the same original supply, sorted differently depending on how close to the sun or how far past it that material happened to settle. Distance decided almost everything else that followed. What varies from world to world is not the recipe, but the proportions, cooked and arranged differently at every stop along the way outward. Every fresh sample returned by a spacecraft, every fresh meteorite picked up from the ground, has so far only reinforced that same conclusion instead of complicating it. One mixture, endlessly rearranged, with only the faintest trace ever added from anywhere else. Trace the whole shape of tonight's route from where it started to where it just finished, and a single line runs through every stop along the way. The evening opened with a plain grey stone that had never been part of any planet, carrying a heat-scarred history frozen inside beads of rock too small to notice with the naked eye. From there, the route crossed the frost line, the boundary that decided which half of the mixture stayed dry and which half kept its ice, then moved through the four dry, rocky worlds, built from whatever that boundary left close to the sun. It passed through a belt where a planet almost formed and never quite finished. Then out among the giant planets that gathered gas, because they built solid cores fast enough to catch it before it drained away. Past them sat an unclaimed shipment of leftover material, stretching out past the last planet, followed by a further scattering of comets, keeping the least altered sample of the original mixture anywhere in reach. Wrapped around several distant moons, that same mixture turned up again as ice thick enough to hold up cliffs and canyons. And running underneath every one of those stops sat a long list of details nobody has fully explained yet, still waiting for better evidence. One cloud, unremarkable in itself, scattered its material across a wide stretch of space. And distance did the remainder of the sorting without asking permission from anyone. Close to the middle, heat burned away anything that could not survive it, leaving dry rock and metal behind. Further out, cold let the ice stay exactly where it landed, patient and mostly undisturbed for billions of years since. Almost none of that original delivery has ever been topped up from outside, at least not in any quantity large enough to change the picture painted here. What looks tonight like a finished system is really just an old one, still carrying the same material it started with, arranged now into its calmest, most settled shape. The mixture that carried this whole evening has finally gone quiet. Nothing out there is waiting to be finished, and nothing is rushing towards some shape it still needs to reach. Rock sits where rock settled. Ice sits where ice survived. Every belt, every moon, every drifting comet keeps its place, unhurried. The way a room settles once the last light goes out, and nobody is left to disturb it. There is nowhere further this particular story needs to go tonight. This small channel exists to keep making slow, quiet evenings like this one. Subscribing takes only a moment and helps more listeners who want exactly this kind of calm find their way here too. Beyond that, there is only rest. The whole system settling deeper into itself, breathing slowly in the dark, content to stay exactly where it landed for a very long while yet.